the mean value theorem and Rolle's theorem. The mean value theorem is another area where we are able to use the derivative of a function to get some useful information from it. Rolle's theorem is a specific application of the mean value theorem, so we're going to start there. And here it is. If f is a continuous function on a closed interval and differentiable on the open interval a to b, where the function values at a and the function value at b are equal to each other, then there's at least one point c in that open interval such that the derivative at c equals 0. And here's why that is, just graphically. If you've got any function, and what we're saying is at the endpoints, the function values are the same. So in this example, the function value at the beginning and the function value at the end are 0. So in between there, the interval we're looking at is from 0 to 2. And in between there, it does some other interesting curvy stuff. But the fact is that at the endpoints of this interval, 0 to 2, the function values are both 0. So what the Rolle's theorem says is that there is some point in between 0 and 2, not including 0 and 2, but there's some point in between 0 and 2 where the derivative must be 0, because the function values at the endpoints are the same. And the reason is, if you drag a straight line, a horizontal line, between those two endpoints of our interval, there has to be some point where that horizontal line would be tangent to our curve, just like it is here. So in that way, there's some point c, some value c, that if you plug it in to the derivative, you're going to get 0, because it's got a horizontal tangent line. Now, Rolle's theorem doesn't necessarily tell us how to find c, it just says that there's some c in there. And when I say in there, I mean within our interval. So between 0 and 2 in this example, there's just some value c, so it looks like maybe, around 0.6 to 0.7, somewhere in there, where our derivative is 0. So try this question. Does Rolle's theorem apply to the function f of x equals negative x squared plus 10x minus 21 on the interval 3 to 5? And I give you a hint, the function is increasing on this interval. Well, if the function is increasing on the interval 3 to 5, that means that the function value at 3 and the function value at 5 must not be the same, because the function is increasing, which means it's just getting bigger as we move from 3 to 5. So the answer to the first question is no, it doesn't. So for Rolle's theorem to apply, we need the function values to be the same at the endpoints. So how about the interval 4 to 6? Well, let's find f of 4. That is negative 4 squared plus 10 times 4 minus 21. And running through the calculations, you're going to get, I believe, correct me if I'm wrong, but I believe I'm going to get 3 there. And then let's do the same at the other endpoint. Now we are plugging 6 in. 10 times 6 minus the same 21. And, well, let's see, this is negative 36 plus 40. That's 4 minus 21. Sorry, 36 minus 60. I'm getting 3 again. So in this case, it looks like Rolle's theorem is going to apply. The other thing we need is continuity, but we're dealing with a polynomial function, so definitely we have continuity on any interval. So now it says find c, and this is something that Rolle's theorem doesn't tell us how to do, so we have to use algebraic techniques. The idea being that we know there is some point c where the derivative equals 0. So let's first figure out what is the derivative. F prime of x is negative 2x plus 10. So if we're going to find c, we need to say 0 equals, so I'm plugging c into my derivative, negative 2c plus 10, and that tells me that c is 5. So it just happens to be right in the middle of our interval. So it does pay to double check that this is indeed in the interval, which was guaranteed by Rolle's theorem. All right, then to answer this question, what about on the interval 3 to 6? Well, no, Rolle's theorem doesn't really apply because the function value at 3, well, let's see, that's negative 3 squared plus 10 times 3 minus 21, and that equals, I believe, negative, oh, actually, I think that's just going to get us 0. Because this will be negative 9, minus 21 is negative 30, and then 10 times 3 is 30. So this function value at the beginning of the interval is 0. At the end of the interval, though, we already calculated that to be 3. So Rolle's theorem doesn't apply. However, because 4, 6, the interval we looked at in the last question, that's a sub-interval of the interval we're being asked about now, and Rolle's theorem does guarantee a c in there, then that c must also be in the interval 3 to 6. So in other words, we don't use Rolle's theorem directly on this interval, but we use Rolle's theorem on a sub-interval. So no, Rolle's theorem doesn't guarantee that on 3, 6 there's a c that works, that gives us a derivative of 0, but it does guarantee it for 4, 6, which is a sub-interval of 3, 6. So we must have a c. And indeed, of course, the same c would work here. C equals 5. Still going to get us a derivative of 0. Okay, let's find an interval on which Rolle's theorem applies to this function, x to the 4th minus 8x to the 3rd plus 12x squared. So in other words, we want to find some values where f of x equals f of x for any two endpoints of an interval. And the easiest way to do this is, let's set f of x to 0. So then find all the points on the function where the y value is 0. So we try factoring. That's always an option. The rational root theorem could also be applied here. But in this case, this one factors nicely, so we can just say that f of x factors into x squared times x minus 6 times x minus 2, so that we know if we plug in 2, or we plug in 6, or we plug in 0, the function is 0. So that means that any of these intervals will be one where we could apply Rolle's theorem, because we know the function values at each of those endpoints is 0. So that means there must be some value between 0 and 2, there must be some value between 0 and 6, there must be some value between 2 and 6 where the derivative is 0. And it could be that the value between 0 and 2 is the same as the value between 0 and 6. But we know that this value between 0 and 2 must be different than this value between 2 and 6, because they're disjointed intervals. So really, between 0 and 6, there must be two different c's that will give us a derivative of 0. Okay, so then we're being asked to find all values of c at which f prime of c equals 0. So really, we're looking for this one, and we're looking for this one. Well, let's play the same game we did before. F prime of x So f prime of x equals 4x to the third minus 24 x squared plus 24x. And of course we want to set that equal to 0. Figure out what x values give us 0 for the derivative. So let me factor out, let's see, it looks like I can factor out a 4x. I'll be left with an x squared minus 6x plus 6. Now clearly, x equal to 0 gives us a derivative of 0. However, that is actually not one of the values guaranteed by Rolle's theorem, because notice it's at the endpoint of any interval, any of these other any of the two intervals that we were looking at. And Rolle's theorem guarantees us something in the middle between the two endpoints. So let's find them, and they must come from this other factor, x squared minus 6x plus 6. So we're going to get one of these values should be the value between 0 and 2, and the other should be the value between 2 and 6. Those should be the two values we get from this second factor. It doesn't look like this is going to factor nicely, so let's just throw it into the quadratic formula. So that's going to be, x is going to be given by, let me not jump the gun here, it's going to be given by 6 plus or minus square root of 36 minus 4 times a times c is 24 all over 2a, which will be 2. Alright, so let's just simplify this a little bit. That tells me x is going to be given by 6 plus or minus square root of 12, it looks like, over 2. And that can be simplified a little more. I'm going to say x is either, well, let's simplify it a little more first. Looks like 2 root 3 over 2. So we have, let's do the positive version first. This is 3 plus root 3. And the minus version, the negative version, is 3 minus root 3. So 3 minus root 3 will be in the interval 0 to 2, and 3 plus root 3 must be in the interval 2 to 6. Okay, so let's be a little more general here. We're talking about Rolle's theorem, but if we broaden our perspective a little bit, we don't necessarily need the two function values to be the same. So Rolle's theorem says they have to be the same, but the mean value theorem says that given any continuous function on a closed interval, a to b, and that is differentiable on the open interval, a to b, then there's at least one point c such that the derivative at that c equals f of b minus f of a over b minus a. And this should look familiar. This is essentially your rise over your run between the two endpoints. So if we can look at a graph of this, if I had any two starting and any 2 points where my function starts and ends, so for example on this graph my interval is 3 to 6, the function values are not the same, but if you look at the slope of the line between those two, that's your rise over your run, the slope of this line. And what the mean value theorem says is that there is some number between 3 and 6 where if I plug that into the derivative, it's going to have the same value as the slope of that secant line. So in other words, the derivative of the tangent at some point in between there is going to equal the slope of that secant line between the endpoints. So here's a quick example. If you're driving and at the 103 mile marker you've been driving for 42 minutes, so which is 0.7 hours, and then at the 170 mile marker you've been driving for 96 minutes, which is 1.6 hours, then your average speed is, just throw that in to the difference quotient here, the function value 170 minus 103 over the time values, the x values, which would be 1.6 minus 0.7, and that gets you 74 and 4/9 miles per hour. Now what the mean value theorem says is that the instantaneous velocity, because that's what we talk about when we're talking about the derivative, the instantaneous velocity somewhere on that trip must have been exactly 74 and 4/9 miles per hour. Now this is essentially the, I guess the method that police could use if they're, if you've ever been driving through long stretches through the desert or in the plains of the United States, you'll see signs that say speed is monitored by aircraft. And what they could be doing, I haven't verified this, but what they could be doing is using this principle, saying that if you drove an average essentially of 74.4 miles per hour between two markers that the airplane above is looking at, then that means at some point, even though they don't have you on radar going that point, that speed, at some point during that speed, during that portion of your trip, you must have been speeding, going 74.4 miles per hour. And so they can use that logic to write you a ticket. So, but don't hate calculus. Slow down. Okay, let's continue. Let's try this example. Does the function 3x to the third minus 4x squared plus 5 meet the criteria of the mean value theorem on the interval -1 to 3? Well, let's check a couple things. Is it continuous? Yes, it's a polynomial. And then is it differentiable on the open interval -1 to 3? Well, yes, again, because polynomials are differentiable everywhere. So it looks like we meet the criteria, and we don't need the function values at the endpoints to be the same. What we need to do, though, is calculate what is the slope of that line between the endpoints. So I'm just going to plug that into our y2 minus y1, or f of b minus f of a, all over x2 minus x1, or b minus a. All right. So first of all, let's get y2. Call that y2. y2, that is the y value at the endpoint, is plug in 3 into our function. And you're going to get 50. And plug in 1. And you get 13. So coming back up here, we get 50 minus 13 all over, oh, and I think I made a quick mistake. This is not 13, I'm jumping the gun here. That is -2. minus -1. Or in other words, 52 divided by 4, which gets us 13. So what we need to do is find the value in between -1 and 3 such that the derivative has a value of 13 at that point. So let's next find what is the derivative function. Well, of course, that's 9x squared minus 8x. And I want to know, where is that 13? So let me call this C now. And we could solve for this. 8C minus 13. And I will go ahead and throw this into the quadratic formula here. That's going to be minus b plus or minus square root 64 minus 4ac, but c is negative, so let's change that to a positive. And 4ac, which is 4 times 9 times 13, I am getting 468 there. And then all over 2a, which is 18. So running through some simplifications, I am getting, well, let's just call this 8 plus or minus square root 532 all over 18. And then, let's see, after pulling something out, I think I'm going to get, well, let's call this 8 plus or minus 2 times square root of 133 all over, let's be a little more careful here, all over 18, divide everything by 2, so we'll get 4 plus or minus square root 133 over 9. And now the positive version is about 1.7. Say this is approximately 1.726, and the negative version will be approximately negative 0.837. So these two values are both in the interval. So keep in mind, the mean value theorem only guarantees that there's one, but sometimes we get lucky and we have two. Okay, so more specifically, I would leave my answer here. The only reason to throw the decimals in is to double check, just to make sure you can see where they are in your interval. But the actual answer I'd be looking for are that these two are the points that we got from the mean value theorem. All right, that's it for the mean value theorem. Give some of the problems a shot and catch me on Discord if you have any questions.